Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 2-4 lesson on graphing polynomials in intercept form. As the title suggests, we're going to be graphing polynomials in this very special form, and then in future lessons we'll tackle the other form. So if you've seen polynomials before, then you know the bad news here is that they come in a wide variety of shapes. The good news is every polynomial can be broken down to basic building blocks. So for your warm-up, pause the video and go ahead and sketch these 6 graphs. And feel free to use a grapher if you don't remember what they look like. Okay, so for each of these, let's go through now. Y equals x, that's just a line going through the origin, starting low, ending high, like so. And now for x squared, we spent like a whole chapter graphing those. That is a parabola going through the origin. For y cubed, you might have to go on a grapher to see this one, and I'll show you on my grapher. So here I am in the y equals of my grapher. I've got x cubed entered in as y1, and I'll just do zoom 6, just a standard zoom to see the basic shape. So we have this interesting kind of going through the origin like a line, but flattening as we go through. So that's the key to that behavior. Now, we're also going to graph the negative version of all these. And if you remember anything about transformations, putting a negative out in front of a function essentially just flips it upside down. So this negative x is really just a slanting down line, like so. Negative x squared is just an upside down parabola. And negative x cubed, we're still going through and flattening. We're just doing it in the opposite direction. Now, the good news, as I say again, is that every polynomial is just going to be a combination of all of these shapes. For the end behavior of polynomials, they all behave like lines or parabolas. For what happens at the x-intercepts of each polynomial, they all behave like one of these 3 shapes, either crossing, bouncing, or flattening as they go through. So let's now go and put it all together. At this point, we're going to work through an example of graphing a polynomial together. And when I say graph, I say sketch here. We're not going to actually do grid lines or anything. We're just going to draw an x and a y axis and make sure things are basically in the right relative locations. So there's 4 features we always go through when we graph these. I call these the fantastic 4 function features. And these features, we've got finding the x-intercepts and the y-intercepts, because that'll give us some points to actually go through. We need something to anchor our graph to the axes. And we're also going to figure out the end behavior and the root behavior. Basically what happens as you go to the far left and far right, and also what happens in between and at each of the x-intercepts. So let's start by finding the roots, or the x-intercepts, or the zeros. They have a lot of different names here, but it all means the same thing. And to find these, you're essentially just setting the function equal to 0 and seeing what zeroes out each factor. So this x plus 1 gives us a root of -1. And we've got +1 for this next factor here, which is actually a double root because it's squared. And for this triple root, because it's cubed, we've got 2 for that root. Now we're just going to put those on the x-axis. And again, we're just putting these in the right relative location. So -1 should go before the y-axis over here on the left. And +1, of course, should be on the right of the y-axis. And +2 should be to the right of +1. So just make sure they go in the right relative places. So that gives us some x-intercepts, but the instructions said to show all intercepts. So we're also going to find the y-intercept. And you only need to do this if the x-intercept, if one of the x-intercepts is not the origin. If one of the x-intercepts is the origin, then that also counts as a y-intercept. But here it wasn't, so we have to find the y-intercept independently. So going through and doing that now, to find the y-intercept, that's going to be what you get when you plug in 0 for x. Because if you plug in 0 for x, you're on the y-axis. On the y-axis, the x value is 0. So if we do that, this x plus 1 is basically just a 0 plus 1, or just as a 1. This x minus 1 squared can basically be thought of as -1 squared. And this x minus 2 cubed is really just a -2 cubed if you have 0 for x. So multiplying all this out, let's see here, -1 squared is just +1, times this 1 is just a 1, over here, negative 2 cubed, that's going to be negative 8. So overall, negative 8 is our y-intercept. And again, just putting that in the right relative location, that should be somewhere below the x-axis down here. All right, so we've got all our intercepts. We know our graph has to go through these points. But where does it start? Above or below the x-axis? Where does it end? And what does it actually do when it gets to the x-intercepts? So let's talk next about end behavior. This is what our graph is doing as we go to the far left and the far right. And this can be boiled down to either kind of acting like a line or a parabola. This is going to be based off the overall degree of the function. If you took all these x's here after all this was expanded out and put this in standard form, what would be the highest exponent? And would the lead term be positive or negative? So those are the two things we're looking at. If you have an odd degree, like x cubed or x to the fifth or something like that, it's going to behave like a line. You're either going to start high and end low or start low and end high. You're going to start and end going opposite directions. If the overall degree of the function is even, then it's going to behave like a parabola. You're going to begin and end in the same places, either beginning and ending above the x-axis or beginning and ending going below the x-axis. So in this case, to find the degree, you basically just look at the x's without worrying about the constants. So we have essentially an x for that first factor. The next factor, if you expanded it all out, is basically going to have an x squared. It's got some other stuff too, but we don't really care about that other stuff. We just care about the highest exponent. And this last factor is giving us an x cubed as its highest exponent. And if we were to multiply these three things together, this is positive, and it's going to be x to the 1 plus 2 plus 3. So x to the 6th, which I'll just say x to the even power. So it gives us a positive x to an even power. Well, that's going to behave like a positive x squared. It's going to behave like a parabola that is opening up. So that's the end behavior of our graph. We're going to start above the x-axis, like a parabola, and we're going to end above the x-axis. And we'll draw that in just a moment. The other important piece, though, we need is that we want to know the root behavior. What's happening as we hit each of these x-intercepts? And we know we have to hit all of them. We also know, and this is very important, that the only place we can touch the x-axis is at these x-intercepts. Because if we were touching the x-axis anywhere else, then it would have already been one of these factors. So for root behavior now, we're basically using the multiplicity of each of these roots, either first, second, or third power, to see if we're behaving like x squared, or x cubed at the x-axis. We're seeing if at the roots we're going to cross, like y equals x, if we're going to bounce, like y equals x squared, or if we're going to go through and flatten, like y equals x cubed. So taking a look at each of these, at negative 1, since that was associated with the x plus 1 factor, which had a first power exponent, we're going to cross just like a line. At positive 1, this next one right here, because that went with this x minus 1 squared factor, we're going to bounce like a parabola, like an x squared. And at 2, because that goes with this x minus 2 cubed, we're going to flatten like an x cubed. So that's what we're doing in each of these. So we've got our game plan here. We're starting with a parabola here. We're starting above the x-axis, and this is what we're doing at each of those x-intercepts. So now let's do it all at once here. So we start up here, and we have to cross at x equals negative 1. We have to go through to hit the y-intercept. So that's going through negative 8. And then we have to go back up, and we're going to bounce at x equals 1. Now we have to come back down and go back up, and we're going to go through and flatten at x equals 2. Now, in terms of where we're ending up, if you take a look here, we're ending above the x-axis, just like our end behavior suggests. But the neat thing is that you actually didn't really think about that as you were going through. As long as you start in the right place and make the right decision at each x-intercept, the end behavior to the far right should take care of itself. Having said that, it's always good to double check to make sure you ended up where you were supposed to be. So I realize we went through a lot of different moving parts in that first example. Here's another example for you to try. Pause the video and see how much of this you can piece together on your own. And as always, I recommend doing your graphs first in pencil before you see the solution. Okay, so let's see how that went. Just like before, we'll start by getting the zeros, the x-intercepts. Those are going to be, for this first factor, we have -3. And our root for the second factor is +1. So we have -3 somewhere to the left of the y-axis and +1 somewhere to the right. Now we look at the y-intercept. So plugging in 0 for all the x's, we're essentially doing -4 times 3 squared times -1. So that's -4 times 9, which is -36, times another -1 gives us +36. So we're going to put that somewhere above the x-axis up here. Now for the end behavior, we essentially have a -x² times an x, which comes out to -x cubed. So we have a -x to an odd power. -x to an odd power is going to behave like a -x graph. So it's basically like a downward sloping line in terms of the end behavior. So this tells us we're starting above the x-axis and ending below it, going down forever as we end. And for the root behavior, we have a double root at -3, so we're going to bounce like an x² at -3. And at +1, we have a single root, so we're going to cross that just like a line. So putting it all together now, we start above the x-axis, we bounce at -3 like so, go through the y-intercept, and cross at 1, and just checking our end behavior, we're ending below the x-axis just like our end behavior said we should. We're going to do one more example. Pause the video and see how much of this one you can get. Alright, so finding the roots, we've got -3, -2 for that next factor, and this last one gives us 1. So -3 somewhere to the left of the y-axis, -2 between -3 and the y-axis, and 1 is somewhere to the right over here. For the y-intercept, plugging in 0 for x, we've basically got 4 times 3 times 2 times -1. So let's see here, this is going to be 12 times 2 is 24 times -1 is -24. So we've got -24 down here. And for the end behavior, we've got basically a positive x times x times x. So that's a positive x to an odd power. So this is kind of like example 2, except this time we have a line that's going up as the basic model for our end behavior. And now for the root behavior, these are all single roots. We don't have anything other than the first power. So all of our roots are going to require us to just cross without flattening, just go straight through at each root. So now putting all this together, we're starting below the x-axis this time, and we are crossing at -3, going back and crossing at -2, go through the y-intercept and cross at 1, and we're ending above the x-axis like our end behavior says we should. So that concludes our lesson on graphing polynomials in intercept form. Next time we'll do polynomials in standard form. Till then, Mr. Sutton signing off.